Madrid, mostly on multimedia. After that, he has done a postdoc in Mitsubishi. No, not a postdoc. I take a job in Mitsubishi.
Yeah.
And then he moved on for a postdoc at the Academy of Science, the Chinese Academy of Science, which is a very prestigious institute in Beijing. And okay, he will mainly talk about this period, the research he did in these BG years. Go ahead.
Okay, thank you very much, Joost, for the introduction. So, yeah, basically I'm going to talk about contextual visual recognition and scene recognition, focusing also in multimodal recognition. So, this is basically what Joost just said. I got my telecommunication engineer degree in the Polytechnic University of Madrid, then the PhD in the Universidad Autónoma de Madrid, working on video summarization and adaptation. My thesis, and basically was the idea was to introduce the notion of scalability in that context, video summarization and adaptation. Then it wasn't postdoc because I hadn't finished yet my thesis, but I started in Mitsubishi, and then after defending my thesis, I continued working there. So it was pre-doc and postdoc. Okay. And then, yeah, I went to China with a postdoctoral fellowship. I stayed there for about 5 years in the Institute of Computing Technology of the Chinese Academy of Sciences. The Chinese Academy of Sciences actually is not only in Beijing, it's all over China. It would be, I think, the equivalent to CSIC here, but at Chinese scale, which makes it the largest research institution in the world. And I was in that particular institute in Beijing. And there I continue working on video summarization and mobile applications, following my previous work in my thesis. But eventually I got involved in other projects related with computer vision. So I've been gradually changing to a computer vision guy. Okay. I've been working mostly in scene recognition, also in food image analysis, contextual food image analysis, and as everyone, using deep learning. And then I'm very glad to be here in the Computer Vision Center. We are working other new topics, like multimodal representations, new topics for me, I mean. So for me it's very exciting being here. So this talk is going to be mostly about this part, scene recognition, food analysis, and deep learning. So the outline is going to be like this. I'm going to divide the talk in two sections. One is going to be related with scene recognition, and the other with food analysis. And each of them I'm going to talk about as different research directions. Okay. So I'll try not to do it too long. So the first direction is scene recognition in the semantic manifold. So first of all, I want to just talk a bit about scenes. What are scenes? So in general, in visual recognition, we want to extract some abstract concepts from the pixels. So we want to reason from pixels, low-level features, from local, let's say, features to global features. And this is also increasing the level of abstraction. And this implies a semantic gap. In particular, for scenes, we have a larger semantic gap because scenes are more abstract than objects. It's a more abstract concept because scenes are composed of objects. So in an object image, we just have the TV set, and in the a scene, we have additional things. Traditionally, this scene recognition has been addressed using this large gap. Has been addressed dividing it in two steps, relying on mid-level representations. So these mid-level representations could be objects, could be just the concept represented in patches, could be topics, they could be explicit or latent, and there are also other, could be parts that are particularly discriminative. So these are just some examples to illustrate the problem of this approach of two classifiers. If we try to model them independently, then we have the problem that we need to have ground truth labels for the mid-level. We need a mid-level vocabulary, and then we need annotations at the mid-level, and this requires local annotations, which are much more expensive than just a label for the whole scene. So this is one problem, and an alternative is using joint learning, which means that, okay, we have two steps, but we just supervise at the top level, and in the same process we have to learn jointly the mid-level representation and the scene representation from the mid-level. So this is usually complex because this is related with topic models, and often they are not scalable to large data sets. And of course, the current approach is just using convolutional networks. But the problem with them is that they require a large amount of data. Well, this is not a problem now. This is no longer a problem because we have these places database and ImageNet, and we have off-the-shelf models, so we can directly use them. But this first research line was more related with addressing the limitation of those two directions. We started this before the explosion of deep learning, and before the places data set appeared. So we focus on this particular work. It's a PAMI paper from 2012, in which they use a method that avoids the mid-level space. This is the idea. We are going to work in local patches, but instead of relying on using mid-level labels for them, we are going to use only the scene label. Okay, so we are going to use these patches, but we are going to assign to all of them the mountain category. Okay, so this is a form of weak supervision, and we are going to, and when we want to classify this image, we are going to do the same. We are going to divide this in patches and then try estimate the category of each class, of each patch, sorry, and each patch is going to be assigned a category, a scene category, and then we are going to combine all the patches, all the descriptors of these patches, because they are already in the scene level, so it's some sort of pooling, and yeah, this is basically the approach. And in this way, we avoid the mid-level vocabulary completely, and of course the mid-level annotations, but we also avoid the joint learning, okay? Because we only have one classifier, this model, because from local patches to image to a scene level, we just do this pooling, okay? But okay, that's to show the difference, to emphasize the difference. If we use a mid-level vocabulary, a mid-level annotation, this region would be annotated with the mid-level category, sky, building, trees, and so on. In this approach, each patch, or in this case region, is given a probability of belonging to one particular scene category. So this is the difference. Okay, but there is always a but, and in this case the problem is that this generates ambiguity in the scene representation. So to explain this, for instance, if you see this patch and I ask you what is the scene here, well, of course you cannot tell. This could be a coast, this could be a mountain, this could be a tall building, but probably you won't say this is a kitchen because of the color. Probably would say this is an outdoor scene. So this representation introduces ambiguity. It actually comes from a mountain. So this is what we found. Well, actually they found this in this PAMI paper, but this is what we are going to exploit in this line of papers. These are the descriptors. Here the representation is well, they call it semantic multinomial. It's just basically a probability vector, and in this probability each dimension represents a scene category. So the first one is suburb, coast, forest. Actually this is a forest. So we see that this bar gives a high probability to forest, but also gives relatively high probability to these other categories like mountain, open country. And here this is an image of an office, and here is given high probability also to other indoor categories like kitchen, bedroom. So this is what I mean with ambiguity. You have a lot of ambiguity in the final representation. So how do they solve this problem? They notice that this ambiguity appears in patterns. They are here. You can see that the same pattern repeats across the same category. This repeats, and also you can see something similar. So they consider this as these patterns that are consistent. They would be the patterns we want to preserve, and we want to kind of isolate them from the noisy patterns that always appear. So this is the main idea. So the idea is that we or they use a second classifier just to solve this ambiguity, because you can model this category from this pattern, these signatures. Okay, so this is basically the idea. We now have two steps, but instead of having low level to mid level and then mid level to high level, we have directly from low level to high level and another step which solves this ambiguity problem. So the motivation is different. In this context we call SMN, semantic multinomial, to these descriptors. Okay, so this is just to introduce the context, because this is not a, let's say, mainstream approach. And then we did several works here with CVPR, pattern recognition, transactional image processing, based on this framework, and exploiting different properties of this space. So the main objective is just to reinforce these consistent concurrence patterns and remove the accidental ones or noise. Okay, so this space is a simplex. Remember that these descriptors are just probability. They sum to 1 and they are bounded to between 0 and 1. So they are lying in this kind of a space, a simplex. But we also notice that this space is the same for patches and for images. Also, this space, being semantic, is independent of the visual feature. And also, different patches, neighboring patches will share this, are represented in the same space and also across scales. So we exploit this idea to do multi-feature combination, to exploit the spatial context, exploit the different scales, and so on. So I want to mention this one in particular, published in CVPR 2015. We model the different patches in the image, all the semantic multinomial descriptors as a Markov random field. So we try to exploit the space. So because this is not Euclidean space, this is a simplex, we use this term. This is just a Markov random field, the potentials. the energy. So we use a negative geodesic distance kernel because this is more suitable to this particular space. And this term is going to be related with the multiple features. This term with the spatial similarity, let's say neighboring patches, and then this is going to combine both. And this is just regularization. We use entropy to regularize. We found that was important. So this is just one example to illustrate this idea. So this is the whole pipeline. Here we extract from each patch, we extract different visual features. Descriptors, gradient related with gradient, with shape, and with color. And from each of them, we extract the semantic multinomial, will be this one. This would be the model we train with them. Just the model I saw before. It would be just this. Sorry, too far. Just this model. So that would be this part, and we do this for each of the three different features. And this is what we propose in this paper to try to filter this noise and to reinforce these consistent co-occurrence patterns. And we do this before the classifier and before the pooling. So this is what happens. These are the different, each row is a different visual feature, and each column is a scene category. And each point here is the patch, the corresponding dimension of the semantic multinomial for that particular patch. So the descriptor would be this point here, this point here, this point here. This would be a one descriptor. And this is the real category of this particular class. So you see that this is very noisy. And actually this particular category doesn't have much high probability, the patches. So we use this Markov random field approach, and this is what we obtain. So here we have removed a lot of noise, which this hopefully will keep these good co-occurrence patterns that we want to model. So this classifier will face less noise in the modeling. And also here you can see that this also increases the probability related with patches in this particular class, which is the ground truth class. So it's also good. So this is just the idea in this paper. I'm going to talk about a second line, which is related with objects and scenes, convolutional networks trained on object and scene datasets, and also the role of a scale in combining them, because we want to combine the knowledge we have in places and the knowledge we have in ImageNet. We want to combine them for a scene recognition, because since the scenes have objects, both places and ImageNet should help. So that's basically the idea. And also we address another problem. We focus on the problem of multi-scale CNNs. And I want to mention first that this observation that changing the scale, making the image bigger and cropping, which means just we take patches at different scales, that is going to induce a bias in the distribution. So in this particular problem where we combine these two knowledge, I'm going to call ImageNet CNN to CNNs trained on object data from ImageNet, and places CNN to the networks trained with places. And there is another, there is an attempt to combine these two data sets and train one network that should know about both scenes and objects, and they call it hybrid CNN. It's from the authors of this data set of places. But the problem with this model is that they don't take a scale into account. So you can see here that you have very big objects, and also you have small objects. So this can be a problem. Another work proposed using from ECCB 2014 to combine deep features but from different scales. So they just resize the image to different scales and they extract patches. And they use the ImageNet CNN just like a black box, and then they combine all these features using some sort of pooling like blood or Fisher vector. In that particular paper they use blood, but the problem is that they are using always the same model here, the same network, which again is ignoring the scale. So we did some experiment just to measure this, and this is what we found. If we this is the size of the image, the full image, and this is also the size of the input to, I think this is AlexNet. So this is the size of the input cropped to AlexNet. So this, if we normalize the size of the patch, this is 100%, and this is the smaller patches in bigger images. So this is the sort of patches we find. So you can see that place is very good when you have a scale, resize them at the scene scale, but ImageNet is bad. But when you go to scenes closer to objects, then ImageNet improves. So this range is more related with scenes, and this range is more related with objects, and also at some point even improves places. And this is interesting because ImageNet doesn't have the same objects, has objects, but has mostly cats and dogs and things like that. Not the objects you find in, not always the objects you find in the scenes, but it still outperforms places here. So we proposed small modifications to try to compensate this bias. So the first idea is just, okay, how about we use places CNN here and ImageNet CNN here. Depending on the range we are, we just use a different model. So this is a hybrid ensemble, but that respects the scale, let's say. Uses the appropriate model depending on the scale. This is fixed, it's not dynamic, but this is by design. We just set it like this. We did experiment with different variants, and also we also tried fine-tuning on patches. So we can also correct this bias by using this fine-tuning. So this is basically the idea. We found that this improves significantly, and it's a better way to combine, to design these multi-scale ensembles, and also a better way to design hybrid ensembles between combining both object and scene data. This was published in CVPR last year. And then this is a different approach in which we work in the first section. I mentioned this framework, the semantic manifold. So you remember I have a Markov random field to model these co-occurrences. So here we extend this to multiple scales, and also using deep features. Well, we also improve the shallow. I mean, the previous work was with shallow features. We also improved the performance in that case, but also we use deep SMMs, in which we use a pre-trained model, and then we use the output of the softmax as the semantic multinomial, the the patch descriptor. Okay, so yeah, and instead of using gradient, color, shape, we use ImageNet CNN and Places CNN. So those are the different features. But the approach is very similar, but in this case we also include in the Markov random field these different scales. So we have because in different scales we have different number of patches, different correspondence. We do this, it's a hierarchical Markov random field, and we solve it using message passing, and it was recently accepted in by transactions on image processing. Then this is a more recent work related with RGBD recognition, multimodal scene recognition. So here, well, just to introduce the common settings, we, in addition to RGB data, we also have depth data. In general, this depth data is also encoded using this HHA encoding, in which gives you a 3-channel image. One channel is related with the depth, another channel is related with the height from the ground floor, and the other is related with the angle with the gravity, I think. So, but the idea is that we transform, well, this encoding transforms the depth information into this 3-channel image, which can be helpful to improve the recognition of the scene. And also it's interesting to note that you can distinguish the shape of the objects here, and you can see borders and so on. So there is certain similarity. But in this setting, the problem is that the data is much more limited than in RGB, especially because it's difficult to capture RGBD data, depth data in particular. While for RGB data, you just crawl the internet and get a lot of images. So before, up to 2015, the largest data set was the NYU version 2, which only had about 800 images for training. So most of the methods were just handcrafted features, and those based on networks didn't really improve this because we have very limited data. In 2015, in CVPR 2015, the SUN RGBD data set was introduced, and now we have around 5,000 images for training. It's still much fewer than this 2.5 million in places, but they tried they fine-tuned the places CNN with this limited data, while with this data set it overfits. In this one works much better and actually outperforms handcrafted features. So the idea is that you take the places CNN and you fine-tune with this, and also you fine-tune with this, so you have two different networks. So this is basically the pipeline that they use in many papers after the release of this data set. This is one example. Actually, there are several papers in CVPR last year that use this pipeline. So you have two different networks, one fine-tuned on RGB data and another fine-tuned on HHA data. And here, for instance, basically the idea is that they typically extract the high-level features and they exploit the redundancy there. And this is reasonable because you have the same filters here and the same filters here. There's likely that there is going to be redundancy here. So this is the main focus of those papers. In contrast, we noticed that might be interesting focusing on these low-level filters. Why? Because these filters don't change when you fine-tune. It's very difficult to change these filters, especially with that so limited data. And these filters are trained for RGB data. So we focus on this part in our work. So this, so we did this experiment. We extracted the outputs of the first convolutional layer of this analysis network trained on places for both the RGB data and the depth data. And we found this. First, this is the source data, places, the first version of places with 205 categories, the validation set. We get this curve. You can find that this is fairly flat, which means that most of the filters, this is, we order them by decreasing value here. So it's fairly flat, which means that most of the filters or all of the filters are is well balanced. They are used almost the same amount of times. Let's say this is the ratio of non-zero values. If you consider other scene data sets, you also find that it's very similar. They have a lot of similarity, the curve. And in particular, this data set, the Sun RGBD, the RGB images, is this purple or violet purple curve, which almost overlaps with the places one. So, but then we did the same experiment with this type of images, and we found this curve, which means that there is a big difference between the both modalities, which, okay, is obvious, but we have a lot of filters. For instance, these filters correspond to these filters that are not really necessary or are not really helping much, and probably introducing noise or are more parameters that we have to train and so on. So we can find this, well, some insight here. For instance, this newspaper has a lot of high frequency information that no longer appears here. So this high frequency information is not really part of the HHA world, let's say. But these smooth gradients, borders, they appear both in RGB and in depth. Here also, I think you cannot see it, but there is this. It has a checker pattern in the back of this seat, of this chair, which no longer appears here. But I think the newspaper is more obvious. So we propose a different approach. Instead of fine-tuning RGB, transferring from RGB to depth, we propose to learn from scratch. Actually, something that was they claim it was impossible with that NYU. So we propose, well, let's try that with Sun RGBD. Since we have fewer training samples, we reduce the size of the network. We need to train fewer parameters, and we also do it in a two-step fashion. So first, we train the first layers of the network. We remove one convolutional layer and transform it in fully connected, and we train another layer with the softmax. So in this case, the receptive field, the input receptive field is smaller, so we use patches instead of the full image to train these first layers. So with this, we achieve two things. We have even fewer parameters in this first stage, and second, we have more training samples by extracting several patches from the original image. So we train first this, then we copy them to the network, to the full network, transform this in a fully convolutional layer, and then add these additional layers and train these layers and fine-tune these layers with the full image. And with this, we get better performance than transferring from RGB to depth and also we don't need to rely on a big data set like places. So we published this paper in AAAI in February this year. And I want to note this. You remember this co-occurrence modeling in the first part? Just want to make this observation. This is also very similar to that. We train with patches. Remember, we trained with small patches and the scene label. So here we are doing the same. We use the image label, and we train with patches. And then we train a second classifier. So you can think that this part as the second classifier. So this has some resembles this co-occurrence modeling. Basically, it's also well, follow similar ideas. And in this direction, the last model we have is related with is also similar idea, but in this case we have a more complex model. We have one model fine-tuned from places, and for depth we have one model transfer from places and another learn from scratch. And in this work we also search for ways to combine these layers, not only at the end but also intermediate layers. And we formulate this as an optimization problem, as a search problem. Yeah, and we submitted this to AGCAI. It's under review. Let's see. And then the other part, maybe I'm going to try to be faster with this. So it's related with food analysis. I also work in food analysis, in particular using the context. And in this particular case, we use the geolocation, the geographic coordinates. So we collected a data set, restaurant-oriented food data set, which means that we crawled several, a website with many restaurants and information about the restaurants. So we crawl several of them, and from each of them we extract the geographic location, the menu, the different items in the menu, and from each item we also obtain several images, and we have several data sets in different cities, Chinese cities. So okay, so this is the type of data we extracted, we collected. So first I want to introduce the problem of food recognition. Food is, well, is let's say an object that is much more deformable than normal objects, rigid objects, and so on. And in this particular scenario, the restaurants, we have many categories. So it's a very fine-grained recognition problem. So yeah, I want to ask how many different categories do you think we have here? I don't know, Joost, how many do you think?
I'm from the north of Europe, so I see 2 dishes.
It's between 1 and 6.
2.
Okay, 2. And how can you?
I would go for spaghetti and Chinese noodles.
Yeah. Yasin? Yeah, Yasin, how many types of food? More than 6. Well, I wasn't expecting that answer, but anyway. Okay, yeah, I think you saw this image because there are actually two classes here. Beef, vegetable, stir-fried noodles, and spaghetti bolognese. So actually there are 2 different types of cuisine, but you see that there is a lot of similarity. But in the same class, there is also a lot of variability. And also, if you focus on these 2 images, there is also a lot of similarity between different classes. So might be sometimes it's difficult to classify them, especially when you have thousands of categories like we had in our dataset. So we propose this idea. Let's try to exploit the contextual information and also try to exploit the knowledge. Assuming that we have a smartphone, we have access to the location and we have access to knowledge from the internet, let's say. So this is our baseline. It's a simple approach in which we have a visual classifier. So this is what we get just from the image. But if we have access to the location, we can guess we are in this area. So how many restaurants we have here? These three. And which dishes they have in their menu. These are their menus. So we just remove the ones that are not likely. So in this case, we simplify this problem, and of course, we will improve the accuracy. But what's the problem with this approach? In particular, with this visual classifier, that is a global classifier. So let's consider this example in which we have 3 restaurants, and each restaurant has two dishes, the blue one and the red one. Okay, so when we train our classifier, we consider globally all the training data. So this is the classifier we are going to obtain. But what happens during test? During test, maybe in our neighborhood there is only this restaurant. So now our problem is much easier than this one. We need to classify in these settings. But the problem is that this is our classifier. We train this classifier. So this is not going to be the best classifier. This will be the best classifier for this particular query. The problem is that this changes for each query, depending on the neighborhood. So if we want to do it like this, we need to retrain a model for each query, which is not practical. So in this work, we try to approach that optimal classifier by using a few classifiers, geolocalized classifiers. So we use the restaurants as anchor points. So we are going to train classifiers for each restaurant and the restaurant in its neighborhood. And then, okay, this is the visual feature, the estimated location, the GPS, let's say, and this will be the dish. So we want to approximate this. And this is a visual classifier, but for the restaurant K. Okay. So during test, we are going to estimate this weight. We pre-train this, and then during train, once we know this, the problem is that we don't know this during training. So during test, we estimate this, try to estimate which restaurants are the relevant, and try to estimate these weights. Okay, so this was published in Transactional Multimedia, and we propose 2 different ways to implement this idea, but I'm not going to go into the details. One of them improves the performance, but also it's much faster than the global classifier. We use SVMs. So when you have many categories in the SVMs, could be very slow. Following a similar idea but a different approach, we propose using a probabilistic point of view in which we model the same variables that were in the previous diagram. Is the same. We have the visual feature, and from that we can estimate the dish category, and we have a model that is a visual classifier. We estimate the location. From that we can estimate the true location, then the restaurant, and then the dish. Using these models, each of them is going to be a model: the neighborhood model, restaurant location model, and the menu. Basically, using this graph, we can decompose the joint conditional distribution, given the location and the visual feature, into these 3 terms, which are related with location, related with the restaurant, and the menu and the visual classifier. So then we just need to marginalize the dish variable, and we can infer the category. But also, we could also infer this one, but we can also infer this one. So this would be restaurant recognition. And if we marginalize this one, then we will have a location refinement. From this location, we could use indirectly the visual information through the restaurants and so on, and improve the localization. So we published this work in Transactions on Multimedia this year. So just to compare the shortlist, the previous approach, the baseline I introduced before, can be represented as in that model. So the neighborhood model would be just like a piecewise model, circular piecewise model. Inside is probability, the probability is 1, and outside is 0. And each restaurant is just a point in the map. So the restaurant model is just a point. In this case, we propose a slightly better model. We use a Gaussian, and for each restaurant, we use a Gaussian also, which means that the restaurant is not just a point, but has some extension. Okay, and this is the last thing I'm going to talk. It's about multimodal recipe modeling. We collected this data set, YAML 28,000. Okay, so, well, we don't have 28,000, we have this many, 27,000, more than 27,000, and we collected from a recipe website, which is YAML. You may know it. So we have images from the recipe, the name of the recipe, the ingredients, and other attributes like the cuisine, Mexican, Italian, and the type of course. Could be the main dish, soups, dessert, and so on. Well, here there are many tasks we can do. For instance, we can find the image given this information, or classify the cuisine given the ingredients and the image. Okay, so these are the type of tasks we have in this work. This is the model. It's based on deep belief networks. The visual feature is this one, extracted with a convolutional network. And then we have the different inputs, the cuisine, the course, and the ingredients. These are the ingredients. It's interesting that they separate visible and non-visible ingredients. We separate these visible ingredients here, which are connected indirectly to the visual feature, and the non-visible ingredients are not connected to the visual feature, are connected later to the type of cuisine and course. So we basically use this model and evaluate it in different tasks. Yeah, so I think that's all. Thank you, and you have any question?
Have you sampled recipes from your last model to see if they produce anything interesting?
Sample.
Sample, like probabilistic sample. I mean, you could cook them, I suppose, in the form of sampling too. Is it a generative model where you could actually produce recipes?
No, actually I was thinking that like you generate a recipe, food image, right? That's what you mean? Or,
no, I mean,
okay, randomly ingredients.
Yeah.
I think no. I mean, this work was done by another postdoc. I don't know the details, but for this work we didn't. I know that they have done other works following this, which I'm not aware of the details, but yeah, our direction is of course trying to generate things, like generate ingredients and perhaps how do those ingredients look like, and so on. Well, I don't know if that was the question. Could be. Okay. Yeah.
Instead of that, maybe I guess that you could generate the most common ingredients for Mexican food cuisine. So if you input the type of cuisine, it should give you the most probable ingredient.
You mean the representative ingredients for a particular cuisine? Yeah, but there are many works on that, I think, not related with images, just with knowledge, data mining, and these kind of things. Yeah, I think that wouldn't be that difficult. I mean, that particular problem. Here, these multimodal problems are more interesting because are more challenging. Yeah.
So that slide that you show the plot for the patches, I have a question that how did you
The beginning.
for the previous one for the plot that was for the different scale of the patches here?
There are patches here. There are patches in other slides.
Plot that you defined.
I pass it. Yes.
No, the next one. Yes.
Ah.
How did you define the aspect ratio for the patches, and are they have overlapping between?
Well, actually, we rescale this to a square image, so they are distorted, but this is also very common. And how I define this, the size of the patch.
Yes.
Well, the input to the network is the same for all the scales.
Or the input images, they have the same aspect?
No, you always the input to the network is always a patch of this size, 27 by 27. So what we do is resize the whole image, but the size of the patch remains constant, fixed. So that's why I include this. This is just the relation between the full image and the size of the patch. Was this question? Your
So
question?
the aspect ratio of the patches or fixed?
Well, we resize the images, and they are going to have aspect ratio 1, okay? And the patches are going to have aspect ratio 1. The only thing that changes is the ratio between the side of the patch and the full image, which is this value here.
The slide of Lasepnik, where the pooling is done, somewhere here.
Sepnik?
Where you pull this one.
This one.
So here, I think the pooling is done by just adding the representations from the different ImageNet networks.
Yeah.
And in your case, that seems to be a strange thing to do. So if you use two different networks, then it's probably not a wise thing to just sum them. Is that what you do? Or
Here.
yeah, in the pooling.
Actually, I didn't try these pooling methods. Probably would work better,
Okay.
but we found that we outperformed them just using max pooling. But it will work better with Fisher vector and these kind of things.
But you're
I don't know how much better,
you're
but
concatenating the
yeah, concatenate them because I made experiments with 1, 2, 6 networks, 6 scales, or 7. Remember, I think, and then the same with the 6 scales from places, 6 scales from. So it was a lot of dimensions. So in that case, I use PCA to reduce the dimensionality. There might be better ways to do that, but because concatenating them would be just too large.
Any other question? Okay, let's take the speaker here.